Lorentz does.
Okay, so thanks a lot for inviting me and giving me the chore to start. So I actually have to say that first I heard for Lorenzo in the 90s when he was working on non-hyperbolic dynamics, and at the time, I mean, I consider him like this brilliant young guy from Brazil, but it seems that I have to revise my opinion. He's not so young anymore, somewhat. So, well, that's more or less happened to everybody, I guess. But still, I mean, he has done since the night a lot of very, very interesting work. And okay, so I'm sure he will continue doing very, very nice work. So that's kind of nice being part of this celebration. So, okay, so in order to start, I think I have to share my screen. So let's see, before I succeeded, let's see if I do succeed.
You are successful.
Okay. So there is someone that has the microphone open. Maybe you can close the microphone unless you want to ask questions. And of course, you can ask questions whenever you want. Actually, it would be kind of nice. So because the problem with, at least for me, with online talks is that I essentially talk to myself, and after some time, I wonder if people are really listening or maybe watching Netflix or something like that. So I find it always, when I teach to students, I know they are watching something else, but maybe it's better with colleagues. I don't know, we will see. All right, so what I was going to talk about is actually didn't know exactly what would be a reasonable topic for this talk, because, okay, I mean, I work in things that are kind of similar to what Lorenzo does, but not exactly the same. So there was not a topic that was exactly, I think, so I don't know, maybe Lorentz gas, Lorenzo, is kind of similar. So, okay, that's the topic. All right, so let's start and let's see what I can say. So just in the unlikely case in which you don't know what the Lorentz gas is, this is a model that was proposed in 1905, so it's more than 100-year-old, and it was proposed by Lorentz as a model for thermal and electrical conductivity in metals. So it has a physical motivation. The idea was originally a periodic array of fixed obstacles, and then you have a gas of particles, which you think of them as electrons, and then this particle collide elastically with the obstacle, right? So in the case in which there is no interaction between particles, then every particle move around without knowing what the other particles are doing. So it is sufficient to understand the behavior of one particle, and then you just get the behavior of the gas as a kind of a superposition of the single particles. So that is very, very simple model. And okay, that was proposed in the hope of having a very simple model to describe this type of phenomena that belong to the realm of non-equilibrium statistical mechanics, a little bit like, for example, the Ising model is a good model to describe equilibrium statistical mechanics. Unfortunately, this model turned out to be much, much harder to analyze rigorously than one would have expected. So there are several results in the so-called low density limit. So low density limit is also called Boltzmann-Grad limit. And this is a situation in which you take the radius of the scatterer that go to zero, the density go to zero, but mean free path, which is the typical time that the particle travel before having a collision, these remain of order 1. Okay, so this situation has been studied quite intensively, and there are very strong results, most recently by Markov and Strognerson. And they use all kind of technique that are based very much on the fact that the obstacles are rare, so the collisions are rare, essentially. So that is kind of the key thing that happens there. But this is not what I would like to talk today. I would like to discuss about the case in which the density of obstacle is actually high. Okay, so because, I mean, if you, I mean, this is like a gas in some sense, right? So very low density is okay if you are maybe in the upper atmosphere, but if you are kind of in water, for example, the density is not so low. Or in a metal, the density is not so low. So you would like to understand what happened with high density. So this is an example, a picture that, you know, show to you what high density can be. I mean, you see these are the obstacle. These are the obstacle, and this is the particle that collides. You see, collides and moves around. So as you can see, this situation is a situation in which the particle cannot fly for an indefinite time without having a collision. There is a maximal time after which the particle will collide with some obstacle. So this is an example. There are many other examples. This is another example that I rather prefer a little bit, in which the situation is a little bit, it's like a square lattice instead of a triangular lattice. It's kind of preferences. I mean, I find it more convenient to make picture. And again, you see, that is the same. You know, there are no trajectories that can go indefinitely without colliding. This is called the finite horizon property. Okay, very well. So, and you can see that the system is kind of defined, is periodic. There are square cells that repeat themselves. And if you have a square cell, then you can play the following trick. You can write the position of the particle as a position inside a torus, and the L is the size of the cell, and K is an element of Z2. So you say, yes, this tells you in which cell you are, and this tells you where you are inside the cell. And this is just a way to write the position of the particle. And that is very convenient because essentially you can, you see, if this is just one cell, and the point is that when you get out here, you end up in a cell that is exactly the same. So you can identify the next cell with the same cell, only now you enter from the opposite side. So you are on a torus. And then it means that you can reduce the study to this torus, billiard on a torus. And the quantity that you are interested in, it is essentially in which cell you are. And in which cell you are is just a situation in which when you cross this, you know that you move to the left, and then you have to add the, so you have the position, how did I call? I forgot. KL. So you have K, this is the cell KL. And now if you get out in this direction, then you are in the cell K plus 0, 1L. So you see, you move here, and if you cross this side, then you have to add this vector. If you cross this side, you have to add the vector. Oh, sorry, this is not 0, 1. I'm sorry, this is 1, 0.
Sorry, Carlangelo.
Yes, tell me.
In your, this is a toy model in the sense that all the obstacles are symmetric, the same size, the same, or not?
Let's say you can have, the point is that the system is periodic. The shape of the obstacle is irrelevant, but I mean, I drew them.
Okay.
They are just round because the program that I use has functions that allow me to draw very easily round obstacles. So I don't have to worry about making pictures, but the fact that they are round is irrelevant. They must be convex. So.
Okay.
So this, if you get out from there, then you have to add the vector 0, -1. So essentially what it means that you can study the dynamics in this billiard on the torus, and the position in the lattice is at Z2 cocycle on the torus. So the problem is somewhat reduced to study a cocycle over an hyperbolic system, which for which there are quite a few techniques that are known. So this story is rather old. The first, well, rather old up to a certain point. Since the model was proposed in 1905, it took almost 80 years in order to have the first rigorous result, which was due to Sinai and Bunimovic. And they proved the subexponential mixing of the Poincaré map. So the Poincaré map is just, for them, in their case, the Poincaré map was this stuff, okay? And they were looking at the map from ear to ear, essentially, from collision to collision. And that is called, so this in bold black, together with the position of with the direction of the velocity, is the Poincaré section. And the Poincaré map is you give me the position, the velocity, and then this gives me the next position and the next velocity after collision. So that is what is called the Poincaré map. And so they proved that the Poincaré map is just a discontinuous dynamical system. It turned out to be hyperbolic, which was proven by Sinai in the 60th century, maybe the early 70s. And then they proved subexponential mixing of the Poincaré map, and this was sufficient to prove that the position of the particle would satisfy a central limit theorem. So this tells you that you start with the particle in some position, and after some time it is distributed as a Gaussian, and this can be rewritten by saying that if you look at the density of particle now, then this will evolve like the heat equation, essentially. So this implies in particular that if you have, if rho is the particle density, rho of t and x, of course, is the particle density at time t, then you have that it satisfies the equation, yeah, Laplacian in x, right? Of rho, and rho of x0 equal the initial density. So this is the heat equation or diffusive equation. So, which is something that you kind of expect, right? Because you expect that if you have some kind of particle distribution, you let it go, it will move and it will diffuse essentially in the environment. So that was kind of the goal from the physical point of view that one wanted to achieve, and it was achieved in this paper. So this paper actually was the template, you know, of a huge research field. I still remember that I first saw this paper when I was a postdoc in Tucson, and Lisa Yang was there. And one day she called me in her office. She showed me her paper, and she asked me, "Do you understand it?" No, she asked me, "Do you know it?" And I said, "Yes." "Do you understand it?" "No." And she told me, "Yeah, I don't understand it either, but I think one should do something in a slightly different way." So that has created an energetic activity trying to do things in a slightly different way than Bunimovic and Chernow did, which was based on Markov partition. And, you know, in 98, Laisang managed to obtain exponential mixing for billiard maps and introduced this now super famous Laisang tower that, you know, have been have been used by all the community to the death now. And after that, especially due to the work of Chernow, this technique was optimized for billiard, and many results were obtained. For example, Sass and Varjo obtained a non-standard CLT in the case in which you have infinite horizon, so the obstacles are not so dense and there are some corridors in which you can travel forever without having a collision. And the fact that in this case you have a non-standard CLT, the central limit theorem was conjectured by Blecher in '92. So you see, it took quite some time to prove that this is in fact the case, not for lack of trying. And then there were many other results having more refined limit theorem by Penet, Dolgopiazza, Svarju, and many others. So this has created quite a bit of activity. And for all these results, it was just sufficient to have a strong result about the mixing property of the Poincaré map. However, I mean, it's clear that this idea that the particles are not interacting is a little bit naive. There is no reason why the particles should not interact between them. Even if they are electrons, they will interact between them, among them. And so there are models that have been, have attracted quite a bit of attention in the last period, in which particles interact, but interact very rarely, because the point is that these places where you can go from one cell to another are very small. Okay, so this is just, you have to imagine these are kind of bigger, and so this is very small. So the interaction between particle here and particle here are extremely rare. So this has been proposed by some physicists, and it has, sorry, I went too far. Yeah, and it has been proposed as a more realistic model in which you hope to get something like heat diffusion. But if you want to study this model, which actually turned out to be not easy at all, it seems that at least that it's not possible to just use the Poincaré map. You need the decay of correlation of the flow, actually. So there is, for example, a nice paper of Balint, Dandoro, Sass, and Toth. So this is Imre Toth, right? Because there is also Balint, Toth, but they are different. One is the last name, this is the first, this is the, I mean, the other is the last name. The first name, this is the, I get confused, whatever. But yeah, they are both students of Sass, but they are different people. So, in any case, I mean, they showed that, I mean, in the fact, if you have decay of correlation for the flow, then you can start at least to say something about this situation in which there are rare collisions. I mean, you cannot go for the moment very far, but at least you can start the machinery. And this has proven much harder. The first result was due to Chernow in 2007. So, you know, if you consider that ergodicity, I mean, if the paper by Bunimovic and Sinai was 81, so it took quite a little bit of time to go from map to flow. And most recently, I have a paper with Baladi and Demers, in which we actually prove exponential decay for a reasonably large class of Sinai billiard with finite horizon. Okay, although there are other classes that are not covered, for example, if you have a corner or stuff like that. So there is still quite some work to do here. Okay, so, but this is not the direction. So this is one direction in which one would like to go for sure. If you have a Lorentz gas, you would like to consider a situation in which the particle, you have many particles and they interact. They are not, you know, non-interacting between each other. But this is not what I would like to talk today, also because I wouldn't have much to say about this. But rather, there is a different direction which is rather interesting, in which one can push the situation. And this is the direction of non-periodic Lorentz gas. And the reason why this is important is that this originally, as I said, was supposed to be a model for like a metal or something like that, right? And physically realistic models, they are not really periodic. They have defect. They always have defect, either because they are there or because you put them there in order to dope the material to have it to make it have some particular properties that you are interested in. So it would be very natural to investigate situations in which you have non-periodic situation, but still you want some translation invariant, and I will discuss later in which sense you have this translation invariance. You may recover this translation invariance. So there are some results already by Sass, Barge, and Ordupiat, in which they get result for non-periodic system, but there the non-periodicity is localized. So you have your periodic lattice, but there is a region in which instead something else happens. So this is a local perturbation. And there they can prove central limit theorem, but essentially the argument uses in a very strong way the fact that the perturbation is localized. Because essentially the argument is, you know, you enter in some region in which you have some scatter. Okay, so if you never get out, then essentially you are confined in some finite region. So you have a finite billiard. If you have a finite billiard, you are ergodic. Then eventually you will get to the place in which you exit. So you cannot stay there forever. And once you exit, then you are in your periodic array, and there you can just move around. So all what you need to know is essentially what is the probability of coming back. So you have, for the periodic array, you have to compute the probability that the particle goes back to 0, for example. And that is a problem that is very well understood for random walk. So you can use a similar strategy and obtain some result. So that is okay. But this is nothing, it's not translation invariant, right? Something happened in a region, you go far away, and then you find yourself periodic as usual. So that's not exactly what I would like to consider. And then in this case, in which you have, you know, you are non-periodic moreover everywhere, more or less everywhere, you cannot do this trick that we did before, that was reduced to the problem to a compact system. So now you don't have a compact system, a compact phase space anymore, and the situation are immediately much, much harder. So what can be done? Well, again, in the low density regime, it's possible to do stuff. I mean, this especially when the obstacles are distributed in a Poisson manner. So you just put the obstacle according to a Poisson distribution in space, and then you look at the particle moving among these obstacles. And these are results for that, essentially first obtaining a kinetic equation that, like a Boltzmann equation that describes the motion, and then showing that if you rescale this Boltzmann equation, you would get indeed a central limit theorem. So that started a long time ago from Galavotti in '96, and then there was a result by Spohn, by Bunimovic, Budirghini, and Sinai. And most recently, there is an interesting paper by Lutzko and Toth. This is the other Toth, by the way. So not Toth of before, this is Balin Toth. And this is in which actually they can get directly central limit theorem in some scaling. Okay, so that's very nice. But again, this is the Boltzmann-Grad limit, the situation in which the obstacles are extremely rare. So we are interested in high density. So what about high density? Well, nothing much is known for high density, unfortunately. There are a few things that are known, and they are essentially a result due to Lench-Trubetskoy, in which they prove recurrence. And then they prove recurrence by proving ergodicity of the process, okay? So it's kind of an ergodicity result for this system. I will describe it better in a second. While on the contrary, the problem of establishing the central limit theorem is completely open. There are essentially no result about that. And not only there are no result about that, but there are very few ideas on how to go about. You see, that's kind of upsetting, no? Because in many situations, you have a situation in which you have some kind of path that you can try to follow, and maybe it's hard, but you have the feeling that if you do put in the work, then you will get the result. So this is what, you know, some people call an energetic obstacle. You have to put energy in order to get to the result. But it seems kind of clear what you have to do. But here is not so clear what you have to do. I mean, so there are some ideas that are missing still. But in any case, I mean, there is something that you can do. So first of all, as usual, when you don't know how to solve a problem, everybody does the same, makes the problem simpler. So one way of making the problem simpler is to try to get to a situation in which you are random, but you have still some degree of periodicity. So you can try to use some advantage of periodicity in your argument. So how can you do that? Well, here is a possibility. So this is the same situation that I was describing before, but the difference is that while these obstacles are periodic, the central obstacles are not. You see, they are in different positions. This is close, this is up, this is a little bit more on the right, and so on and so forth. So this is a situation in which still you have a periodic cell structure, but the system is not periodic. So you can try to hope, there is the hope that you can try to use a little bit the periodic structure and still start to understand something about non-periodicity, about what happens when the system is not periodic. Okay, so that is somewhat the little idea that I had. I mean, let's, you know, divide the problem in, make the problem a little bit easier and see what one can say in this situation. All right. So in this situation, you see, since you have this cell structure here, you can still look at the billiard in a cell. So now you have a cell. And now I want to use a different Poincaré section. My Poincaré section would be this one, okay? And this will be my Poincaré section, P1 to P5. And you see, the point is that if I cross P2, for example, then again, as before, I want to keep track of the position as Z is the position, it tells me which cell I am. And if I get out from here, then I have to add 1, 0. And this is my new position, the new cell in which I am. The problem is that I cannot think that if I get out from here, then it's like getting in from P4. Because unfortunately, the cell that is here will have the central obstacle in a different position. So it's true, I get again in a cell, but this cell is kind of different. I mean, it has the Poincaré map is always the same because it's this. For simplicity, let's take this always the same radius. It's not necessary, but I mean, just make life easier. And then you have that this has always the same length, but it is in different situations. So while the Poincaré map is the same, is X, of course, you could consider a situation in which the Poincaré map is different, right? This will make your life even hard. For example, it could be that these obstacles are not exactly periodic. Some is bigger and some is a little bit smaller. This will make your life much, much harder. So let's start with the simplest possible case and see, because if one is not able to say something in the simplest possible case, then to think about harder case seems to be a little bit, I don't know, useless. So the Poincaré section I want to consider is always the same. It's this X, which consists of these 5 things, of course, together with the outgoing velocity, all right? And now I have a finite set of possible obstacle positions. For example, think the simplest possible situation, you have two obstacle positions. Two obstacle positions. The obstacle can be position 1 or position 2. And then this A will be just 0 and 1, for example. And now, to each alpha, which tells you where the obstacle is, it corresponds to the Poincaré map. Of course, you see, the Poincaré section is always the same, but the Poincaré map is not, because, for example, you can enter from here with this velocity, then you do this, you do that, and you get out from here. So the Poincaré map, oh, sorry, actually, the Poincaré map, since this is part of the Poincaré map, will just be from here to this, from this to this, okay, from this to this. But the point is that, you see, the position of this obstacle changes. So the Poincaré map will be different according to what the position is. So you get that the situation in which the Poincaré section is always the same, but the Poincaré map changes according to the position of the central obstacle. Okay, so this is the situation. And then you want to introduce the idea of random environment. So in random environment, what it is? I mean, oh, sorry, this is, I was taken by kind of an excess of optimism. This is not D, this is 2. We are in Z2. Yes, I mean, that is kind of a very annoying thing about billiard. I mean, you know, maybe you wonder why all these people that talk about mixing in billiard, they always talk about dimension 2. Okay, the reason is that in dimension 3, we are not able to prove anything, but just anything. So situation is completely a disaster in dimension 3. So there are problems that there are some conditional results which are better than the theorem. If it is true, then it is true, but not, it's extremely better. I mean, so that is a little bit annoying, but anyhow, that's life. This is an outstanding problem in billiard, try to prove quantitative mixing for three-dimensional billiard, for example. Okay, so sorry, so that's why this D was totally ridiculous. So that is just 2. And so you take A to the Z2, it means, what does it mean, A to the Z2? It means a situation in which you have your R2 is full of cells, and in each cell you decide where the obstacle is. So you need to decide if in each, so the possible space of all the configuration of the obstacle is 0, 1, if you have just two positions for the obstacle, to the Z2. And this is the space of all the possible environments that you can have, okay? You are interested in a specific environment, of course, but you don't know which one. If you consider them as defects, then you have no idea what the defect will be. You just have some, you want just to have some probabilistic idea. And the idea is that you have all the possible environment, and then you put a probability measure on them. And the simplest probability measure that you can put is just independent probability measure. For example, you can realize it by, at each cell, you have a coin. You flip the coin, you get 1, you put an obstacle, you get 0, you put the other obstacle. And you do it for every single cell. So you have these infinitely many coins, you flip them and you see what happens. And that is an environment, the one that you produce, okay? And the probability of this environment is specified by this probability measure PE. So it's not necessarily that you want to consider this independent case, but maybe you want to consider some ergodic translation invariant probability measure, but certainly you want ergodicity, certainly you want translation invariance. So that is the type of system that you want to consider. And then what you want to study is the motion of the, yeah.
I have a, that is, what you have is a skew product or something like this.
Not, if you wait 1 second, you will see that it's not a skew product. Yes, just wait 1 second.
Okay, thank you.
And so, I mean, what I'm interested in is the motion of a particle in a fixed environment. Okay. But of course, you see, it cannot be in all environment, because if you allow me to put the obstacle where I want, I can just put them and make the particle go wherever I want, right? When the particle arrives in a certain cell, I put the obstacle in the place that I like, and then the particle will go wherever I want. So it means that it's too much all environment. What I want to say, make statement for almost every environment. So I want to make statement PE almost surely. That is the goal, okay? And this type of model are called deterministic walk in random environment, because the particle move in a deterministic manner, but the environment is random. So that is just name, deterministic walk in random environment. Okay, so let's answer the question of Lorentz. So how does it work, the dynamics? So the dynamics is, there is the Poincaré map X, and then you have, again, ZD. Okay, I'm sorry. Z2, okay. So, and then you have Z2. So it means that if you want to specify a position, you have to give me a coordinate X that tells me where you are inside the cell, and the coordinate Z that tells me in which cell you are. So if you tell me, if you give me X and Z, then I can write Z L, where L is the size of the cell, plus X, and I know where I am in R2. So this is exactly like before. Okay, but the dynamics, how it looks like. It looks like this. I am in a certain cell Z. Okay, and then I look at my X. Maybe X is here. Then if X is here, I know that I am here, and so I will go in this cell, which is Z plus 0, sorry, 1, 0. Because I know that being here means that my position is this and my velocity is that. So I'm just going in the next cell. Okay. And now, because it means that I just reached from this cell, I reached this thing. Here there are the obstacles. Okay. So I reached this point here. So my velocity is pointing outside the cell. So I enter in the next cell, and then here there is stuff, and then maybe I do this. And this is my new position. So what do I have to do? I have to update the position that tell me in which cell I am, adding the vector EX. What is the vector EX? It simply tells me in which element of the Poincaré section I am and adds the right vector. So if I am in this section here, I add the vector 0, 1. If I am in this section here, it means that I am still inside the cell. So I have to add the vector 0 because I don't change cell. If I am here, for example, I will have to add the vector 0, 1. Okay. So this tells me to which cell I move. And this tells me in the cell in which I arrive, which is this one, which dynamics I have to use. Okay, this is the Poincaré map for this cell. Okay, and because this tells me this omega of Z, it just tells me which omega is an element of this, all the possible environments. So omega tells me what the environment are, where the obstacles are, and so omega Z tells me what is the position of the obstacle in the cell Z. So this tells me what is the position of the obstacle in this cell, the cell in which I arrive. And there I have to apply the corresponding Poincaré map. And so, and this is...
Sorry. But you know that where is included the direction? Because you see that the vector, once you hit the section, you go in some direction.
Yeah, but yeah, that's correct. But the point is that you see,
don't need to...
the point is that X is made is really QV. Q is the position, okay, and V is the is the direction. Yes. So I write it X because I'm a lazy guy, but that is that's what it is. So I was saying, yeah, this is the answer to Lorenzo. You see, this is not a skew product because these dynamics depend on Z. If the obstacles are all the same, then this map is always the same, and this is a skew product. And that is the case in which things are periodic, because the central obstacle is always in the same place. So everything is periodic, and then you get a skew product, because the map F does not depend on the size in which, the place in which you are, and then you have the map Fx, and then this is just updated, and that is a cocycle. So it becomes a cocycle only in the periodic case. If it is not periodic, it's simply not a cocycle, which makes life slightly miserable for people that want to study it. So I don't know if this answers your question. So
I think that you have a skew product.
this you call a skew product? Ah, sorry, cocycle, a cocycle.
A skew product, I think.
Ah, okay. So I don't know. I mean, I'm sorry. I mean, okay. Yes, then it's a skew product. I never remember what I was.
It's okay.
I mean,
you're right.
Whatever. I mean, I always have trouble with names of things. I mean, what I want to say is that it is not a cocycle over a map. Okay. All right, so that is the system. So you see, it's a system on a non-compact space, and that is what you want to study. There is something more that you have to say. What is the initial condition that you want to consider? Of course, you see, as usual, when you want to consider limit theorem for dynamical system, you cannot start with a real precise initial condition, because if you just decide the initial condition, the particle will go somewhere, whatever it goes, there will be no probability whatsoever. So you need to start with some probability distribution in order to have some randomness in the system. And but you would like to have the minimum amount of probability of randomness possible, and the minimum amount of randomness possible is to say, okay, I start from a certain cell, let's say the cell 0. So I know that at the beginning I am in the cell 0. What I don't know is where I am in the cell 0. So in order to describe where I am in the cell 0, I have some distribution, probability distribution with the density H0, which should be, as usual, regular, at least C1, or maybe C alpha, but I mean, not just continuous. So that won't help. So this is some regular probability distribution at time 0, and this tells you what is your distribution in the cell 0. Okay. All right, so now we have a dynamical system. We know what is the initial distribution. We know what is the dynamics. This is the dynamics. And now we want to study this dynamical system. Okay. So
I'm sorry,
yeah.
would you be starting, for example, by just picking uniformly a point in X?
Well, I mean,
Cell 0.
The point is that no, it is just H naught. H naught. Yeah, you could start taking H naught equal 1. Then it would be uniformly. Yeah, you can think that. Yes, okay. You can think that. If it makes you happy, this is okay.
Okay, great.
Okay, very fine. It's easy to please you then. I mean, there's not much of a change. All right. So now I will. So this is my model of deterministic walk in random environment. And now, what I would like, ideally, what one would like to prove is a central limit theorem for the position of the particle. Okay, and as I was saying before, there are not many ideas about that, but there are certain things that you do in the compact case in order to get the central limit theorem. And the things that you have to do, first step is to prove some kind of decay of correlation, some kind of mixing. That is the basic ingredient in all this proof of limit theorem for the compact case. So that is the first thing that one has to do. No, I mean, in the waiting to have a good idea, then maybe you can start to do some work that you know that it will be needed anyhow. So that is. So first of all, I mean, you can prove. So if you want to look at the statistical property of this system, the first result was due to Lenci in 2003. He proved the ergodicity of this system. Okay. So actually, one should be a little bit more precise. The system that where is it? The system that he looked at, it was not exactly this, because this you see is for each omega. So the system that he looked at was the some f that acts on x, z, and omega actually, and it acts on fz like f omega of xz, and omega is just time translate. It's just translation. So it is time translation of omega. Sorry, not time translation. It's translation by z. I'm sorry. There is not enough space to write. Okay. So you want to translate by something that depends on this w of z omega. So essentially, the point is that if you are in this size and you move here, okay, so you move with the vector 1, 0, then you want to translate omega to 1, 0 in such a way that this well, yeah, you don't have to write it exactly like that. Then. I'm sorry. I have to be a little bit more precise.
Well, if you're keeping track in the second coordinate of what cell you're in, then
yes, that's
your
what
formula for the first.
Yeah, that you have to put z. You have to. I want to look at. Yes, I want to know that the 0, 1 is the zero component of this guy is the cell in which I am, the omega in which I am. So this is kind of, so the phase space, it is x times z2, x times z2 times omega. Okay, and then you have a probability measure. Here you have PE, and then here you have Lebesgue. Okay, and, well, Lebesgue on x. Okay, here you have just the counting measure. So the system is slightly more complicated, but it doesn't matter. I mean, essentially, it proves Lenci proves ergodicity for a proper system, and this is enough to show that you have recurrence, right? Meaning that you eventually come back to the original to some place. I mean, if you start from some place, you will come eventually, but maybe very rarely, but eventually come back to that place. Okay, so ergodicity more or less was done. The next step is mixing. Okay, that's the next thing that you would like to prove, mixing some kind of decay of correlation. That is what is done in compact case, in the compact case. But unfortunately, now you have a problem. What does mixing mean? Because in a non-compact case, you know, if you just look at the correlation, they simply go to 0. And it's not really clear what it is, the right definition of mixing in the non-compact case. So, for example, you can look at Aronson's book, which is a book about non-compact dynamical system, and then there's a lot of discussion about the problems. And more recently, Lenci has tried to make some sense of certain situation. I mean, defining local mixing, local global mixing, global mixing. There are some paper by Dolgopiat in which he tried to make sense of all these things, but the situation is not so clear. Yet, I mean, instead of entering in this black hole of trying to understand what is in general mixing for all kind of system with non-compact space, maybe it's better to ask, but what we really want to compute? I mean, what is our goal? Well, our goal essentially is to compute stuff like this. This is, given the environment omega, you want to know what is the probability of seeing a certain path. So you look at your, imagine that you look at your walk from far away, and you don't want to keep track of where you are in the cell. You want only to keep track of which cell is visited. That's it. So if you want to keep track of which cell the particle visits, then you want to know what is the probability of seeing a certain path. And what is the probability of seeing a certain path? Well, you know, you just have the dynamics, which is just your dynamics f omega, you know, to power n, starting from 0 x naught, because you start from the cell 0 with some x naught, which you don't know what it is. And now you have this random variable x n vn. And then you want to compute the probability, you have to say that this history actually give rise to this history. And when does this happen? Well, for example, x naught, sorry, let me just, okay, let's say here I am, this is the 0 cell, and let's say that the next cell is this one, which is the cell 1, 0, okay? What does it mean if my story is 0, 1, 0? So this is 0, 1. It means that I have gone through this stuff. I will call these gates because they allow you to go from one cell to another. It means that x0 belongs to this guy that was maybe P1, P2, I don't know, P2. Okay, so it means that if you define WK as the change in position, change of cell, tells you which cell you are in the cell ZK, you go to the cell ZK plus 1. The difference, the jump that you do is WK. And it means that your position was in fact in here. It could not be in here because otherwise you would have ended up in this cell, but you know that you end up in this cell because you are looking at the probability of this path. So it means that you have to compute this integral in which you have the particle must go through certain places, or if you want to see it in a different way, it cannot go to other places. So it's like a system with holes, because if the particle goes here, then you disregard it. You don't want to consider it. You kill the dynamic. If it goes here, you kill the dynamic. If you go here, you kill the dynamic. If it goes here, then you follow it. And then you have to check that next one is the right place that allows you to go to the right cell. So this is essentially a dynamical system with holes, okay? And I will go back, or open dynamical system if you want. I will go back in a second to what it means. But now let me just say, what kind of mixing result may I want on these quantities? Well, I want something that is kind of a loss of memory. So imagine that I look at the thing, I look at the system, and I know that it is in certain state omega of the environment, and I know that it went to Z1 up to Zn plus 1. And now I want to know what is the probability that goes to a nearby cell. So because if I am in the cell Zn minus 1, then next time I can go in 4 different cells, and I want to know what is the probability of going, for example, on the cell of the left. And of course, this quantity is computed using these quantities, okay? It's just a conditional probability. So, you know, if you know these guys, you can compute this guy. And what do you want? Well, you essentially want that it doesn't matter. It depends, you want this probability to depend only on the recent past. So you want that it does not depend, for example, if n is large, it should not depend from what you did the first time, the second time, the first time, right? Because essentially You have to look at the picture in this way. You are here and you had some history, okay? And now imagine that you have a different history, this one. Okay, so this, you started from here and you arrived there. And now, well, of course, now you have to translate the environment, right? Because you want this to be 0 now. Okay, so you translate the environment in the way in which you have to translate it. And now you have a situation in which you start here and you arrive there, and the situation in which you start here and you arrive there. It should make no difference whatsoever, because from here to here, you see exactly the same. In this part, you see exactly the same obstacle. You see exactly the same dynamics. The only difference, starting from here or starting from here, it means that when you arrive here, you have different distribution, probability distribution inside. Because here you are in the same cell, but the probability distribution, here you start with H0, here you start with H0, but here it will be something which depends on this history, and here it will be something that depends on this history. So you start with completely different probability distribution, but then you have the same dynamic for quite a long time. So if you have some loss of memory, then you expect that it doesn't matter if you start from here or from here. And so it means that if you decide to start from here with H naught, which is another probability distribution, which is totally stupid, as stupid as the one that you obtain from here and the one that you obtain from there. If you start here from H naught, then you should see exactly the same thing than if you started from there. And that is exactly what it says. This is the probability of this path starting here with the probability H naught. This instead is the probability of this path starting with the probability H naught here. And what you would like to show is that these two probabilities are the same apart from something exponentially small, which is proportional to the length, to the time that you spend in this common trajectory. Okay, this means that in some sense the past is irrelevant. You don't have to worry about what happened in the far past. You have just to watch what happened in the last collisions, and that is enough to have information about the probability of going in the next step in one place or the other. So this is a loss of memory, and that is actually most reasonably the type of result that you want to have. At least, I mean, all the vague possible ideas that I'm aware of in order to try to prove something, they always end up needing this type of result in one way or another. So this is, I call this loss of memory, and this is what I would like to prove. Okay. All right. And now, so I told you that oops, wow, it's much later than I thought. Oh, I'm sorry. So, okay, I will not be able to say what, okay, sorry. So this one is the formula for this probability, but you can just integrate by part, and then you can get this other formula. When this one is the transfer operator for the map L alpha, this is the characteristic function of the set PW, and that is what it is. Okay, and if you look at this, normally, if you want to study the decay of correlation, typically you want to study this object, transfer operator applied to something, and this will go to some limit, in some topology to some H star, which is the invariant measure. You start from some measure, any measure that is reasonable, and then you iterate this transfer operator and you get the invariant measure. So this is just the push forward of a measure by the dynamics. And the push forward of a measure by the dynamics is given by this stuff. And this is exactly, you see, what I was saying before. This is a sequential billiard with large holes. Okay, so that's what you want to study, sequential billiard with large holes. And there are results for small holes, there are results for sequential billiard, but there are no results for large holes. And if you want to attack this problem, I see two possibilities. One is to use standard pair, one is to use Hilbert matrix. And what we decided to do together with Mark Dammers was to use Hilbert matrix, because there were already several results that, sorry, I'm accelerating because I see that my time is up. There were already several results in the literature that showed that it was possible to use Hilbert metric in order to deal with large holes, especially this paper by myself and Veronique Maume-Deschamps. So, and also there were papers that showed that you could deal with billiard. So, what is the idea of this Hilbert metric? The idea of this Hilbert metric is the following. You find a cone of in functional space, a convex cone, and you want an operator that sends this convex cone inside itself. Okay. Essentially, this is what you want. You have a convex cone of function, you want to send it inside itself. I mean, given a convex cone, if you take the section, it is convex. And there is some way of defining a metric, which is essentially you take 2 points, you take the line going through the point, you get to the boundary, and then you have 4 points now, and you take the cross product, and you take the logarithm of the cross product. And this is a metric. It's kind of amazing, but that is Hilbert. I mean, it's not some random guy that invented this stuff. Okay, so this metric is such that if the image has finite diameter in this matrix, then you get a contraction of the transfer operator. And then you can prove that it converges to something, right? Because it keeps being mapped into smaller and smaller cones. So the point is that find a cone, and here it is. It's awful. I'm sorry. I have no time to explain it, but the point is that it depends on certain parameters, and in fact, it gets contracted in some cases. I mean, this is just some cone of function. I mean, so, okay. I mean, I'm out of time, so I will just stop here, just saying that this cone of function is contracted in certain cases, and so it's possible to prove this loss of memory for certain class of this billiard. I mean, I have no time to enter more in detail and explain. I'm cheating a little bit, but okay. I mean, I'll stop. Sorry for taking more time than I wanted.
Thank you. Do you have questions?
Carlangelo, I have a question. Usually when I know that you're not in a skew product, but the people that work on the skew product, you have the condition of the fiber maps. The yes. Condition of the fiber maps here is to have this contraction in the cones or something like this, or?
So, I mean, you see, you could, yeah.
Or maybe I am doing the wrong question. Okay.
No. You see, the cone, you have to be careful. The cone is a cone of function. It's not a cone in the tangent space, right?
Oh,
so well, you are, okay. Because you apply the transfer operator to it. So you are, but you are right in some sense, in the sense that you could look at the space of densities instead of the point, right? This is, I mean, essentially Kolmogorov taught us that it's a good idea to look at the evolution of measure rather than the evolution of points. So if you look at the evolution of measure, what is the dynamics of measure is given exactly by this operator, okay? So now you have a situation that is, you have a fiber. The fiber is the density. You apply this operator and it gets to a density again. And now in this fiber, you have some contraction. So it is more or less something similar to what you are saying, but you have to glorify the system and look at it in functional space instead than in the usual phase space somewhat. But that is exactly what happened. You have a cone of densities, you push it forward, and then you get a new density that is in a smaller cone, you push it forward, and so on and so forth. So what does it mean? It means that if you want to know what is the density at a certain time, in a certain, so you are here. You want to know which kind of density do you have, knowing that you have certain past. What do? You go here, and then you take a density here inside the cone, okay? And this density will be mapped inside here a little bit in a smaller cone. But then you could go one step backward and take the cone here of density. This one will be mapped here in a smaller cone, and this will be mapped here in an even smaller cone. So as you go backward, this will converge to something. And so this will tell you that here you have some densities that depend on a certain amount. I mean, if you are willing to allow for some mistake, then you just have to go back some time. No matter from where you start, you always get more or less the same density at this place. And so you know what is the probability distribution of the particle in your now in your cell, and this allows you to say something about the probability that it jump left, right, stuff like that. That is, so it becomes very similar to, essentially becomes very similar to a standard random walk in a random environment, which is a very hard problem anyhow. So it's not that you solve the, essentially this, all this technology takes you to a situation in which you are in a situation very similar to a standard random walk in a random environment.
Thank you.
Okay, thank you. I don't think we have time for more questions. You have the chat possibility. We have the next talk. I think we would continue without break.
Let me stop my sharing.
And Sebastian